Hi, I'm Tuukka Korhonen, and I will talk about integrating tree decompositions into decision heuristics of propositional model counters. And this is joint work with Matti Järvisalo. What we do in this paper, we consider the problem of counting the number of solutions of a given CNF formula. So in other words, propositional model counting or Sharpshot. And what we do in this paper, we take this this kind of old model counter Sharpshot and we modify it so that we use tree decompositions in the decision heuristic of Sharpshot. So we do variable selection based on partly based on a tree decomposition that has preferably a good width. And what we see is we see when we do this tree decomposition in decision heuristics, we see that we get a significant improvement over state of the art on a standard benchmark. So this improves even compared to other model counters that use tree decompositions. And then we get in this model counting competition this year this model counter Sharpshot TD. Based on this work, it got first places in 3 out of 4 tracks in this competition. Okay. So Sharpshot TD, this is our modification of Sharpshot. So basically, we can see how original Sharpshot works. It first does pre-processing and then it does counting based on this sharp TPL algorithm, where basically it's like TPL, but then you have a close learning and component analysis and component caching. Okay, and what we do in Sharpshot TD, our modification of Sharpshot is again, it's important to have this pre-processing first, and then for the pre-processed formula, we compute a tree decomposition with this FlowCutter software, and then we integrate the tree decomposition into variable scores. So we make the variable scores to take this tree decomposition into account, and then we run exactly the same counting with just somehow altered variable scores. Okay, so but now I'll talk about what actually are tree decompositions. Let's look at this. Here's a CNF formula, and here's a primal graph of this formula. So basically, in the primal graph, what we have is the vertices. They're the variables of the CNF, and we have an edge if there is some clause in the CNF that contains both of these variables. So, for example, we have an edge between x1 and x5 because there is a clause that contains x1 and x5. Okay. And and here's an example of a tree decomposition of this primal graph. So basically, what is a tree decomposition? It's just it's a tree where each node is a back containing some vertices, which in this case are the variables, and then we need that for each edge there is some back that contains both endpoints of this edge, and we also need that for each variable it appears in a continuous subtree. So for example, x1 appears here and x5 appears here, so it appears in a continuous subtree. Okay, and we say the width of a tree decomposition is the size of the largest back minus 1. So basically, it's trivial to have a tree decomposition where you put all variables in the same back, but it's not so easy to have a tree decomposition where this size of the large spec is small. So this measures the quality of a tree decomposition, how much it tells about this graph or about this CNF formula. And then yeah, we say tree width of a graph, or CNF is the minimum width of a tree decomposition of this graph, or this graph from this CNF. Okay, and now basically what we implement in Sharpshot TD is it's a tree decomposition guided variable selection. So how tree decomposition guided variable selection works is when we before we branch, we need to select some variables. So what we do, we select so we have some formula, and here we have some tree decomposition of formula, and we select the variable that appears closest to the root in this tree decomposition. So we say tree decomposition, it has some nodes as a root and other nodes below it, and yeah, and now, for example, here we first select x2. So in this example, let's say we branch, we set x2 equals 1. Okay, then by unit propagation we get x3 equals 1 also. And now we have to do variable selection again because we don't have unit propagation. And now again there's a variable in the root which we haven't branched from, so we select that. And so we branch from x5 at this point. And now, when we have branched from everything in this root, this formula it becomes disconnected. And in Sharpshot, it's already implemented that there's a component analysis. So Sharpshot breaks solving this into breaking into two different subproblems. So one component with x1 and x4, and another component with x6. Okay, and let's say now we go into this component with x1 and x4. Now in this component, the variable closest to the root is x1. So next we branch from x1, and note here, yeah, we cannot branch from x4. So yeah, it's unique that the x1 is closest. So we branch from x1 next, and yeah, then we got the empty formula, and then everything happens again. But yeah. Okay, so this is tree decomposition kind of variable selection, and basically it's quite well known that this standard TPL Sharp TPL algorithm, like what Sharpshot does, if it implements component analysis and component caching like Sharpshot does, it works in time 2 to the 3 width times polynomial in the size of the formula when we use tree decomposition of width W for doing this variable selection. Okay. And here are some examples of what do these widths of tree decomposition look like in real instances. So this is from the model counting competition. So basically there are quite many instances where tree width is like less than 25, and it's like if you put 25 here, you can see it's already like it shows that okay, you can solve this in quite reasonable time. This theoretical stuff, and then like in reality, it's this formula, it gives quite high running time, but we can see that even when the width is quite large, this doing this based on tree decomposition, it helps a lot. And these widths there, like most of them have we can get the tree decomposition of width like less than 60, say. yeah, so there are 100 instances in total. Okay. Yeah, but now how we actually do this tree decomposition based variable selection in Sharpshot TD. How we do it? Okay, so in Sharpshot, what we have is we have this this score array, which has yeah, for each variable some score, and what always happens is Sharpshot it looks at this active component and selects always the variable with the highest score. And in standard Sharpshot, this score it basically has two components. So it's an activity score, like visits, like a activity score, plus a frequency, so number of occurrences of this variable in the current formula. Okay. And in Sharpshot TD, we modify, basically we implement this tree decomposition based variable selection by a very simple modification to this score. So now what we do, we subtract at this term this c times dx, where c is some positive constant, and dx is the distance from the root of the tree decomposition that we have to the closest back containing this variable x. Okay. And now if we put c to a very large value, we can see that this always selects the variable that is closest to the root. So this is purely, so if you put c very large, this selection is done purely by looking at this tree decomposition. Okay, and then if we put this constant c small, close to 0, then the selection, this is same as in standard Sharpshot. So we have this constant c with by using it, we can alter how much we take this tree decomposition into account in this variable selection. And of course, this theoretical bound, it will not hold for anything else than large values of the c. But we can see that we actually get good results in practice by using some intermediate values of this constant c. And so basically, what we do is we first we compute the tree decomposition. We see what does the width look like, and then choose this c based on it. So if we get very bad tree decomposition, it's close to standard Sharpshot. But if we get very good tree decomposition, then it's then it uses this tree decomposition a lot. Okay. Yeah. Yeah. So now let's go to look some experimental results. So the setting we have in this paper is we have 2,424 instances merged from these two sets. So this is basically some yeah, from the hours of D4, and this is some set that has been used in this model counting competition. And yeah, we put time limit of 2 hours, a memory limit of 16 gigabytes. And also an important thing here is we always we use 900 seconds for computing tree decomposition with this flow-cutter software, and we take this 900 seconds into account in this result. Yeah, so the running time will be like lower bound by 900 seconds. And but here I just want to know that using 60 seconds in 900 seconds for computing this tree decomposition would give kind of similar results. Okay, but yeah, let's see this this cactus plot, this overall comparison of these model counters. So this is like where we have in the x-axis how many instances are solved, and in the y-axis the time in which this instance was solved. And so overall, Sharpshot TD and Kanak TD, they solve the most instances. And Kanak TD, it's just the same modification as Sharpshot TD, but instead done on Kanak. And this Kanak is another model counter that is basically it's some modification of Sharpshot. So we see that okay, if we do this, then basically Kanak and Sharpshot seem to be very equivalent. Okay, and yeah, then there is D4 and a lot of other model counters, and I would say also here is we have a C2D TD and mini C2D TD. So C2D and mini C2D, they by default they use some tree decomposition, but here we also try to put this, and they also like you can give a tree decomposition to them to use. So here we use the same tree decomposition that we use for Sharpshot TD also for C2D and mini C2D, and we see that okay, their performance improves a bit, but not to the level of Sharp TD. Okay, and yeah, so basically, yeah, Sharpshot TD is also more than 90 instances more than other counters. Yes, and yeah, here you can see there's this 900 seconds used for computing this tree decomposition, so it's taken into account in this time. So it looks quite weird in this plot, but you could as well use 60 seconds to get a very similar result. And in the competition, we actually use 2 minutes for computing tree decomposition. Okay, and yeah, here's some comparison of Sharpshot and Sharpshot TD grouped by the width of the used tree decomposition, and here we exclude the time used for computing tree decomposition just to make this result look more readable. Yeah, and okay, now the thing is basically what happens is when we have when this tree decomposition that we use has a width of like less than 30, then we see Sharpshot TD. It's always better than Sharpshot. It always gives an improvement over Sharpshot, or stays the same. And basically, like if you look at for instances where you have tree decomposition of width less than 30, Sharpshot TD. So here's a number of instances. Here's a Sharpshot number of instances solved by Sharpshot in 2 hours, and here's number of instances solved by Sharpshot TD in 2 hours. So we see like Sharpshot TD solves all but 2 instances of this width, while the normal Sharpshot, there are like more than 100 instances it doesn't solve. And this is not very surprising that this works well for instances where we have a very good tree decomposition. But what's more surprising, at least to me, is that it seems to work also very well for instances with where we have decompositions of width like from 30 to 150. So also in these cases, a Sharpshot TD actually it gives overall improvement compared to Sharpshot. And but you can see in this scatter plot. So here's running time of Sharpshot, and here's running time of Sharpshot TD. That in this class from 30 to 150, there are also cases where the Sharpshot TD is much worse than Sharpshot. But if you actually look at timeouts, you can see that there are a lot more cases where Sharpshot TD is better than Sharpshot. And yeah, and then for instances with more than with higher than 150, there is really not that much of an effect.